In this video, we're going to look at how we can deal with transformations in two dimensions where the origin is not fixed. Now, we know that if we've got a transformation of the form xy goes to a matrix times by xy, then that transformation does not move the origin. However, there are lots of transformations that do not fix the origin. For example, we could do a translation of 3, 5. We could do a rotation about any point other than the origin. Or we could do a reflection in a line which doesn't pass through the origin. And what we're going to try and find is two possible ways of representing such transformations. So let's start by considering a translation. So in the diagram we have the translation which moves everything 2 in the x direction and 5 in the y direction. And we can write this clearly as being the point xy goes to xy add 2, 5. In other words, we can say the point xy goes to the point x dash y dash, where x dash is x plus 2 and y dash is y plus 5. Now, we could say that x dash is 1x plus 0y plus 2, and that y dash is 0x plus 1y plus 5. And we can see that these two rules for x dash and y dash are given by the first two rows of the matrix multiplication 1, 0, 2, 0, 1, 5, 0, 0, 1 times by x, y, 1. In other words, we are able to represent a translation in two dimensions by using a 3 by 3 matrix. Now let's see one or two other examples of where we can use a 3 by 3 matrix to represent a transformation in two dimensions. So let's consider first of all the transformation consisting of a reflection in the y-axis followed by a translation of the point 4 minus 2. Now if we think in terms of what's happening in terms of a sketch here, the blue triangle there is our initial object. The dotted triangle, image 1, is what we've got after the reflection in the y-axis, and then the green triangle is the result of translating the dotted triangle by 4 minus 2. Now we're going to try and chase through what happens to a general point xy if we go through this transformation. Now the first part of the transformation is a reflection in the y-axis. Now for a reflection in the y-axis, we know that the origin is fixed, so there should be a 2 by 2 matrix which represents a reflection in the y-axis. And it's easy to find this matrix because all we need to do is think about what happens to 1, 0 and what happens to 0, 1. So first of all, if we do a reflection in the y-axis, 1, 0 becomes the point minus 1, 0. And the point 0, 1 is actually on the y-axis, so when it's reflected it stays on the mirror line as the point 0, 1. So we've got the point 1, 0 becomes minus 1, 0. That's the first column of my matrix. The point 0, 1 stays as 0, 1. That's the second column in my matrix. So for our general point xy, the general point xy, when we do the reflection in the y-axis, becomes minus 1, 0, 0, 1 times by xy, which simply gives me minus xy. And then when I do my translation of 4 minus 2, the point minus xy goes to minus xy plus 4 minus 2. In other words, it becomes minus x plus 4, y minus 2. So the transformation takes the point xy to the point minus x plus 4, y minus 2. So we could write this as xy goes to x dash y dash, where x dash is minus 1x plus 0y plus 4, and y dash is 0x plus 1y plus minus 2. And we can write that in the matrix form as x dash y dash 1 equals the matrix minus 1, 0, 4, 0, 1, minus 2, 0, 0, 1 times by x, y, 1. So we've got a matrix transformation, a matrix representation for the transformation consisting of a reflection in the y-axis followed by a translation of 4 minus 2. If you look carefully at this final matrix, you can see that the 4 numbers in the top left-hand corner of the 3 by 3 matrix are precisely the 4 numbers in the 2 by 2 matrix, which represents the reflection in the y-axis, which represents the first part of the transformation. And the 2 numbers on the right-hand side at the top of the 3 by 3 matrix, the 4 minus 2, are precisely the numbers involved with the translation that we have got. And we can generalize those 2 results. If we've got a transformation T which consists of the transformation given by a 2 by 2 matrix, xy goes to ABCD times xy, followed by the translation PQ, then that transformation, that overall transformation, can be given the matrix representation xy1 goes to the matrix ABP CDQ 0, 0, 1 times by xy1. So the ABCD is precisely the matrix that we had for the first part of the transformation, and the PQ is precisely the translation that we've got for the second part of the transformation. Be careful though, if the translation comes first and the matrix transformation comes second, the result is very different. So let's have another look at another example. Suppose we're considering the transformation consisting of a reflection in the line x equals 4. Well, if we draw a diagram to try and work out what's going on, if we take an arbitrary point, xy, then its image is an equal distance the other side of the mirror line. So what we've got is the line going through xy, hits the mirror line at 4y, and then the image is the point x dash y dash. Now clearly what I dash is going to be exactly the same as y, because the mirror line is x equals 4. Now we know that x dash minus 4 is the distance of the image away from the mirror line, and that's going to be exactly the same as the distance of the mirror line away from the point xy. and that distance of the mirror line away from the point xy is 4 minus x. In other words, we've got x dash is 8 minus x. So we've got x dash is minus 1x plus 0y plus 8, and y dash is 0x plus 1y plus 0. And this means that we've got the matrix representation for the reflection of x dash y dash 1 equals the matrix minus 1, 0, 8, 0, 1, 0, 0, 0, 1 times by x, y, 1. And if we like, we could also regard this matrix as being the matrix for a reflection in the y-axis, which we know has got matrix minus 1, 0, 0, 1, followed by a translation of 8, 0. So in other words, we've seen that a reflection in the line x equals 4 is the same as doing a reflection in the y-axis and then following it up by a translation of 8, 0. Let's now have a think about if we want to try and do a rotation of 90 degrees anti-clockwise about the point 2, 3. Well, again, we'll start with a diagram to try and see what's going on, and the diagram needs to show the point 2, 3, which is the centre of our rotation, together with an arbitrary point xy. Now, when dealing with rotations, particularly rotations through right angles, it's very convenient to deal with an L shape, with the sides of the L shape being parallel to the axes. So there's my L shape joining the centre of the rotation to our arbitrary point xy. And when I do the rotation, the L shape will look like that. Now, on the original L shape, the length of the x step is x minus 2. And that will therefore be the length of the vertical part of the image L shape. And that means that in moving from 2, 3 up to the image point, I am going to be moving up by distance x minus 2. So I can say that y dash, that's the y coordinate of the image, is going to be 3 plus x minus 2. In other words, it's going to be x plus 1. Going back to the original L shape, we have got a vertical movement, or a movement in the y direction, of y minus 3. When we rotate the L shape, that vertical movement of y minus 3 becomes a movement to the left of distance y minus 3. So, in moving from the centre of rotation to the image point, x dash, y dash, we have got an x step of negative y minus 3. So that means that x dash must be 2 take away y minus 3. In other words, x dash is 5 minus y. So we've got x dash is 0x plus minus 1y plus 5, and y dash is 1x plus 0y plus 1. So we've got the representation for this rotation as being x dash y dash 1 is 0 minus 1, 5, 1, 0, 1, 0, 0, 1 times by xy1. For our next example, we have a transformation T which consists of 3 operations. First of all, a translation of 5 minus 2, then a reflection in the line y equals x, and finally an enlargement of scale factor 3 and centre the origin. And we have to find a matrix representation for the transformation t, and we also have to find the fixed point of the transformation t. So, if we're going to find a matrix representation for the transformation t, we can start thinking about what happens to a general point xy. And if we start off with the general point xy and translate it by 5 in the x direction and minus 2 in the y direction, we're going to end up with the point x plus 5, y minus 2. We've then got to do a reflection in the line y equals x. And doing a reflection in the line y equals x simply switches over the existing x coordinate and the existing y coordinate. So once we have done the reflection in the line y equals x, we are going to have the point whose x coordinate is y minus 2 and whose y coordinate is x plus 5. Then we've got to do an enlargement of scale factor 3 and centre the origin. Now all an enlargement of scale factor 3 and centre the origin does is multiply the x coordinate by 3 and the y coordinate by 3. At the moment our x coordinate is y minus 2, times it by 3, we get 3 lots of y minus 2, and at the moment our y coordinate of our point is x plus 5, so when we do the enlargement that becomes 3 lots of x plus 5. In other words, the point xy ends up at the point whose x coordinate is 3y minus 6 and whose y coordinate is 3x plus 15. Now our matrix representation will be that the vector xy1 must go to, now our first row needs to give us 3y minus 6. In other words, we've got 0x plus 3y minus 6. So the first row needs to be 0, 3 minus 6. The second row, when I do the multiplication, has got to give me 3x plus 0y plus 15. So I need 3, 0, 15. And then the final row has got to just give me 0x plus 0y plus 1. So my matrix representation is xy1 goes to 0, 3 minus 6, 3, 0, 15, 0, 0, 1 times by xy1. Now to find the fixed point of the transformation, it's easiest just to use the fact that we know that the point xy goes to the point 3y minus 6, 3x plus 15 under this transformation t. Now if the point PQ is a fixed point of t, then the image of PQ is itself PQ. In other words, we know that PQ, that was the object point, must be the same as the image point, which is 3q minus 6, 3p plus 15. So we've got a pair of simultaneous equations. We've got p equals 3q minus 6, and we've got q equals 3p plus 15. Tidy those up into the standard form for simultaneous equations. We've got p minus 3q equals minus 6, minus 3p plus q equals 15. And then solve either using your calculator or any of the standard simultaneous equation methods. We obtain p is minus 39 over 8 and q is 3/8. So we've got the fixed point is the point minus 39 over 8, 3/8. Our final worked example gives us a transformation T which consists of a stretch of scale factor 3 in the x direction, followed by a translation of minus 2, 5, followed by a clockwise rotation of 90 degrees about the origin. We've got to find a matrix representation for T. We've got to find the coordinates of the fixed point of T. And we've got to find the image of the line y equals 6x minus 12 under the transformation T. So in order to find the matrix representation for T, we're going to do very much the same as in the previous example. We're going to start off with the general point xy and think about what happens to that as it goes through the different processes. Now, a stretch of scale factor 3 in the x direction has got matrix 3, 0, 0, 1, and all it does is it simply multiplies the x coordinate by 3. So the point xy is ending up at 3xy. We're then doing a translation of minus 2, 5. So when I do the translation of minus 2, 5, the point 3xy becomes the point 3xy add minus 2, 5. In other words, becomes the point 3x minus 2, y plus 5. And then, finally, we've got to do our clockwise rotation of 90 degrees about the origin. Now, 90 degree rotation about the origin takes 1, 0 to 0, minus 1, and it takes 0, 1 round to 1, 0. So the matrix for a clockwise rotation of 90 degrees about the origin is the matrix whose first column is 0, minus 1 and whose second column is 1, 0. And when we apply that to the point whose coordinates at the moment are 3x minus 2, y plus 5, we get our final image is the point y plus 5, 2 minus 3x. So the transformation T can be described by xy goes to y plus 5, 2 minus 3x. Y plus 5 is the same thing as 0x plus 1y plus 5. 2 minus 3x is the same thing as minus 3 times x plus 0y plus 2. So our matrix representation is xy goes to x dash y dash, where x dash y dash 1 is equal to 0, 1, 5, minus 3, 0, 2, 0, 0, 1 times by xy1. So we know the transformation is described by the point xy going to the point y plus 5, 2 minus 3x. So the fixed point, if the point AB is the fixed point of T, then the image of this point is itself. In other words, we must have B plus 5 equals A and B equals 2 minus 3A. And this pair of simultaneous equations can be rewritten as A minus B equals 5 and 3A plus B equals 2. And using a calculator or solving them in the normal method, we end up with A equals 7 over 4, B equals minus 13 over 4. So the fixed point of the transformation T is the point with coordinates 7 over 4 minus 13 over 4. And for the final part of the question, again we're going to use the fact that the transformation is described by xy goes to y plus 5, 2 minus 3x. A typical point on the line y equals 6x minus 12 is the point P, 6p minus 12. The image of this point after the transformation t is going to be x dash y dash, where x dash is y plus 5, that is x dash is 6p minus 12, that's original value of y, add 5, so we've got x dash is 6p minus 7, and y dash is 2 minus 3x, so the final y value is 2 minus 3 times the initial x value, so that's 2 minus 3p. Now if we look at the x dash equation, we've got x dash is 6p minus 7, so we can say that p is the same thing as x dash plus 7 divided by 6, which means we can now substitute that into the equation for y dash to get an equation linking y dash and x dash, but without any p's in the equation. So doing that, we've got y dash is equal to 2 take away 3 times x dash plus 7 over 6. In other words, it's 2 take away a half of x dash plus 7. So we've got y dash is minus a half x dash plus 2 minus 7 over 2. In other words, we've got y dash is minus a half x dash minus 3 over 2, which is perfectly good format for the final solution. So we've got the image of the line y equals 6x minus 12 under the transformation t is going to be the line y dash equals minus a half x dash minus 3 over 2, or if you like, we've got 2y dash plus x dash plus 3 equals 0 as the equation of the image. Now to finish this work, there's an exercise here, and you might like to either pause the video or even perhaps take a screenshot of this page and have a go at the 2 questions on this page, and you will find that a little bit later on we move on and we get 2 more questions, 3 and 4, like that. If you've got time, have a go at all 4 of the questions. If you haven't got time, make a start with number 1 and see how far you can get with them. Good luck.